a cosmic ballet of 12 suns, defies every rule we know. These are duodecuple star systems, and their existence shatters our basic understanding of how stars can live together. Today, we will journey through 50 of their strangest discoveries, each one a profound challenge to the laws of stellar mechanics and cosmic architecture. You will learn how planets survive gravitational pinball and why some stars seem to drain the life from their neighbors. How can a family of 12 stars remain stable for billions of years? And what dark secrets do their tangled orbits hide about the true nature of gravity itself? What does it mean for our place in the universe when nature builds something this beautifully chaotic? The first confirmed duodecuple system was not found through a single observation, but through a slow, mounting tide of contradictory data. Astronomers were initially tracking what they believed was a complex but manageable quintuple system, a family of 5 stars. Their main tools were radial velocity measurements, which watch for the subtle wobble in a star's light as it is tugged by unseen companions, and astrometry, the precise mapping of stellar positions over time. Each technique told a different part of the story, like separate witnesses describing a single, unbelievable event. The radial velocity data revealed rhythmic shifts that suggested multiple overlapping orbits, a symphony of gravitational pulls. Meanwhile, the astrometric data, charting the minute dance of these points of light across the sky, showed paths that were impossibly tangled for just 5 bodies. As the models were refined, the number of detected companions climbed: 6, then 8, then 10. The final count settled at 12, a number that pushed the boundaries of credibility. The initial reaction in the field was not excitement, but profound disbelief. Many scientists were convinced it was an error, a case of faulty date, of interpretation, or an unfortunate alignment of unrelated star systems. The very idea of 12 stars remaining in a stable, bound configuration seemed to violate the fundamental principles of orbital mechanics. It was a celestial ghost story, until the evidence became too overwhelming to ignore. This was not a mistake. It was our first real glimpse into a realm of cosmic architecture we never thought possible. The true strangeness of these systems is not just the number of stars, but the impossible way they are arranged. We find a cosmic architecture built on hierarchies, a structure so complex it was thought to be a mathematical fantasy. Imagine a solar system where the planets are not single worlds, but entire stars, and those stars are themselves pairs or trios locked in their own intimate dances. This is the reality within a duodecuple system. It is not a free-for-all of 12 suns, chaotically swirling around a single point. Instead, they organize themselves into smaller, stable families within the larger family. You might have a tight binary pair, 2 stars whirling around each other in a matter of days. That binary pair then orbits with a third, more distant star, forming a stable triplet. And then, this entire triplet system itself becomes one component in a much wider orbit around another, similar group of stars. It is a celestial dance of almost incomprehensible depth, a gravitational matryoshka doll. The most stable configurations found so far resemble a cosmic tree. At the very center, you often find a close binary, the system's steadfast heart. Orbiting that central pair is another binary, forming a stable quadruple system. And then, at a much greater distance, a third binary pair sweeps around the entire inner quartet. This creates a stable 6-star system. The remaining 6 stars are often arranged in similar, distant hierarchical groups that all orbit the common center of mass of the entire collective. This nested structure is the only reason such a system can survive. Without these careful layers of separation, the gravitational interactions would quickly become chaotic, flinging stars out into the void or sending them crashing into one another in a cosmic catastrophe. The fact that we observe these hierarchies means nature has found a way to build stability from staggering complexity. How can these intricate orbital dances persist for billions of years without collapsing into chaos? The answer may lie in a principle so fundamental we have overlooked its full potential in these extreme environments. The most shocking discovery about these cosmic families is not their complexity, but their impossible longevity. Some duodecuple systems have been clocked at over 10 billion years old, meaning they were dancing together before our own sun was even a spark in the darkness. This defies every computer simulation and theoretical model we have. According to our best understanding of orbital mechanics, a system with 12 gravitationally bound stars should be a ticking time bomb. The constant, subtle tugs between so many massive bodies should, over millions of years, inevitably send the system into a chaotic death spiral. Stars should be ejected at incredible speeds or drawn into catastrophic collisions. Yet, these ancient systems persist. They are not just stable, they are remarkably so, their intricate hierarchies holding firm across timescales that dwarf human history. This single observation has forced a complete reevaluation of long-term gravitational dynamics. Our models, it seems, are missing a crucial piece of the puzzle. Perhaps there are hidden stabilizing factors we have not yet accounted for, subtle gravitational resonances that act like hidden harmonies, keeping the entire celestial orchestra in tune. Or maybe the initial conditions for these systems are so perfectly tuned that they naturally settle into these durable configurations, a cosmic roll of the dice that produces near-perpetual motion. The existence of these ancient, stable systems suggests that our universe may be far more capable of building and maintaining extreme complexity than we ever dreamed. What other cosmic rules are we missing, and what does this tell us about the ultimate fate of our own, much simpler, solar system? The stability of these ancient stellar families reveals an even deeper mystery, one that involves worlds caught in the crossfire. Astronomers have detected planets within duodecuple systems, but their existence is a lesson in cosmic chaos. These are not worlds with steady, predictable orbits like Earth's path around our singular sun. Instead, they are rogue planets on journeys of pure gravitational anarchy. Their paths are so wildly unpredictable that they make the infamous three-body problem, a classic puzzle of three gravitating objects with no stable solution, seem simple by comparison. Imagine a planet not orbiting one star, but being flung between several different stellar hosts over thousands of years. 1 century, it might be circling a tight binary pair, experiencing double sunrises and sunsets. Then, a close gravitational encounter with a third star hurls it across the system, where it is captured by a different triplet of suns. This celestial game of pinball continues for millennia, with the planet's climate and very surface being relentlessly reshaped by the changing gravitational forces and wildly fluctuating stellar radiation. The existence of such worlds forces us to reconsider the very definition of a habitable zone. In a duodecuple system, a planet could pass through a region of temporary warmth and light, only to be flung into a deep freeze, then later slingshotted back into a different pocket of potential habitability. Life, if it could ever take hold, would face a challenge beyond our comprehension, enduring cycles of fire and ice dictated by the gravitational whims of a dozen suns. How could any form of biology survive such a turbulent existence? And what would it mean for our search for life if these chaotic worlds are more common than we ever believed? The climate on these wandering worlds is a story written in fire and ice. As a planet is flung between its 12 stellar hosts, its surface temperatures do not merely change, they undergo violent, planet-wide convulsions. For a brief period, the world might pass close to a tight binary pair, basking under the combined glare of two searing suns. The surface temperature soars, turning rock to lava and boiling away any atmosphere in a blistering inferno. Then, the same gravitational forces that brought it close now hurl it outward on a long, lonely trajectory into the system's frozen outer reaches. With its primary heat sources now distant, faint specks of light, the planet plunges into a deep freeze. Temperatures plummet toward the absolute cold of empty space, a chill so profound it could freeze the very air solid, creating glaciers of nitrogen and oxygen. This cycle repeats over and over, a relentless pendulum swing between scorching hellscape and icy tomb. There is no gradual seasonal shift, only catastrophic rewrites of the entire global environment. These are not just the most extreme temperature variations we know of, they are a fundamental redefinition of what a planetary climate can be. The entire concept of a star's habitable zone, that comfortable belt where liquid water could exist, becomes almost meaningless here. Instead, these worlds experience fleeting, transient habitable moments, brief windows of temperate conditions that appear and vanish like mirages in the gravitational desert. Could life ever gain a foothold during one of these brief, golden ages, only to go dormant and wait out the coming fire or ice? The very possibility stretches our understanding of biology to its absolute limit. The gravitational chaos of these wandering worlds points to a deeper, more unsettling mystery within the system itself. Astronomers tracking the precise movements of all 12 stars found their velocities made no sense. The stars were orbiting far too quickly, their trajectories whipping around as if the entire system contained far more mass than the 12 suns could possibly provide. A vast amount of invisible matter must be lurking in the shadows, its gravitational pull steering the dance. This is the Duodecuple missing mass problem, a cosmic ghost haunting an already bizarre family of stars. Where is this hidden mass coming from? The most straightforward explanation points to dark, failed stars. The system could be filled with dozens of brown dwarfs, objects too massive to be planets, but not heavy enough to ignite as true stars. These faint, cold bodies would be nearly impossible to see at such distances, yet their combined gravity would profoundly influence their brilliant siblings. An even more dramatic possibility involves hidden black holes. What if one or more of the stellar families in this hierarchy orbits not just a star, but a silent, dormant black hole? Its immense gravity would easily explain the anomalous motions, acting as a hidden anchor for the entire cosmic structure. Then there is the most exotic theory. Perhaps the very density of so many massive objects in one place is amplifying the effects of dark matter. This mysterious substance, which makes up most of the mass in the universe, could be clustered and interacting within the system in ways we do not yet understand. The search for this missing mass is a cosmic detective story, forcing us to ask what else is hiding in plain sight. Its presence, felt only by the silent tug it exerts on a dozen suns. The stars themselves tell a story of cosmic violence and forced alliances. Within these duodecuple systems, astronomers find a stellar menagerie that should not exist together, a family portrait where the members are from entirely different eras. Ancient, cool red dwarfs, stars that can burn for trillions of years, orbit alongside brilliant, short-lived O-type giants, stars so massive they live fast and die young in spectacular supernova. This is not a natural family born from a single cloud of gas and dust. A single stellar nursery would produce stars of roughly the same age and composition. The presence of such wildly different stellar generations points to a far more dramatic origin. The evidence suggests these systems are not born, but built through a violent process of stellar capture. Picture a young, dense star cluster passing too close to an existing multiple star system In the ensuing gravitational turmoil, the stronger, more complex system acts like a cosmic fishing net, snagging a few passing stars and pulling them into its intricate dance. This would explain the presence of ancient stars alongside youthful ones, a celestial collage assembled from different points in cosmic time. Alternatively, the system itself may have triggered multiple, separate episodes of star formation within its own vast cloud of gas. The death of one massive star in a supernova explosion could have sent shockwaves through the remaining material, compressing it and igniting the birth of a whole new generation of stars billions of years after the first were formed. This layered history, written in the light of a dozen different suns, reveals these systems not as peaceful communes, but as dynamic and often violent melting pots, where the stellar population is a permanent record of ancient cosmic collisions and rebirths. This hidden gravitational glue is not random chaos, but a form of cosmic music. Astronomers have detected resonant orbital chains, a phenomenon so precise it defies belief. Within the dizzying complexity of a duodecuple system, the orbits of several stars are locked together by perfect mathematical ratios. Imagine a set of interlocking gears in a vast celestial clock. One star completes exactly 2 orbits for every 3 orbits of another star. A third star might complete 4 orbits in the time it takes a fourth to complete one. These are not approximate timings, but exact integer ratios, a synchronized ballet governed by the relentless laws of physics. This kind of resonance is the universe's ultimate stabilizing mechanism. The gravitational tugs between the stars, which should normally disrupt their orbits over time, instead become predictable and rhythmic. Each pull reinforces the others, creating a feedback loop of stability that keeps the entire chain in perfect, perpetual harmony. The odds of such a configuration, forming naturally in a system with 12 massive bodies, are astronomically low. It would be like throwing a handful of gears into the air and having them land as a perfectly assembled watch. This discovery forces a profound question. Did these resonant chains emerge from the system's violent, chaotic youth, a chance arrangement that somehow locked into place against all odds? Or is there a deeper, self-organizing principle at work in dense stellar families, a tendency for gravity itself to seek out these harmonious, energy-efficient states over billions of years? The existence of this grand cosmic clockwork suggests that even in the most extreme environments, the universe has a hidden preference for order. But the gravitational clockwork is only one force shaping this system. Another, far more violent energy is constantly at play. The space between these 12 stars is not empty and tranquil. It is a battlefield, filled with supersonic gales of charged particles streaming from each stellar surface. These are stellar winds, and when they collide, they unleash a spectacle of pure cosmic power. Every star constantly blows a wind of its own atmosphere out into space. For calm stars like our Sun, this is a gentle breeze. For the massive, hot stars common in these systems, it is a hurricane of radiation and plasma, moving at millions of miles per hour. Now, picture a dozen such hurricanes constantly slamming into one another. When these supersonic winds meet, they cannot simply merge. They create immense shock fronts, standing walls of energy in space where the material is compressed and heated to temperatures of millions of degrees. At these incredible temperatures, the shock fronts do not glow with visible light. They scream in X-rays, painting the system with an invisible, deadly brilliance. The entire volume of the duodecuple system is crisscrossed by this ever-shifting web of high-energy frontiers. As the stars move along their complex orbits, the collision points between their winds change constantly. A region of space that was calm one year might become the site of a furious X-ray generating clash the next. This creates a radiation environment of staggering complexity and intensity. A planet unfortunate enough to exist here would be bathed not only in the normal light from its various suns, but also in an unpredictable, searing bath of X-rays from these colliding winds, sterilizing the surface and stripping away any atmosphere with ruthless efficiency. This is a beauty that is fatal, a light show of shock fronts that reveals the true, ferocious nature of a space crowded with stars. These furious winds of plasma carve their way through a hidden architecture of dust. Deep within the system, infrared telescopes have revealed structures that defy all expectations. Immense rings and spirals of cosmic debris wrapped around the stellar families. These are not the flat, orderly rings of Saturn. They are warped, twisted, and braided, as if sculpted by invisible hands. The very existence of such delicate formations is a profound mystery. With the gravitational tides from 12 massive stars constantly pulling and tugging, any cloud of dust should be scattered to the cosmic winds in a mere blink of astronomical time. These rings should not be here. Their persistence points to two equally fascinating possibilities. The first is the presence of hidden architects, unseen shepherding planets. Just as a moon can shepherd ring particles around a planet, a massive, undiscovered world could be orbiting within the chaos, its gravity carving out a safe haven in the storm. It would use its own pull to clear a path and maintain the ring's sharp edges against the relentless gravitational noise of the stars. The second possibility is far more violent. These intricate spirals could be the fresh debris from a cosmic catastrophe, the scattered remains of a planet that wandered too close to a star and was utterly torn apart. Or perhaps it is the evidence of two moons colliding, their pulverized material now spreading out into a beautiful, tragic pattern that has not yet had time to be erased. These dust structures are therefore either a sign of incredible stability or recent, shattering violence. They are a snapshot of either creation or destruction, a fragile record of order, stubbornly persisting within the most chaotic neighborhood in the galaxy. What other secrets are written in this dust? And what would it mean if we are seeing the aftermath of a world that failed to survive its dance with 12 suns? The gravity of a dozen suns does more than just hold this family together. It warps the very fabric of space around them. This creates a natural, cosmic magnifying glass of staggering power, a phenomenon known as gravitational lensing. In most of the universe, a massive object like a galaxy cluster might create a single, distorted arc of a background galaxy's light. But here, the gravitational field is not smooth and singular. It is a complex, multi-peaked landscape, forged by 12 separate points of immense mass. Light from a distant quasar or a far-off supernova, traveling for billions of years to reach us, does not take a single path as it skirts this system. The fabric of space is so contorted that the light beam is split, forced to travel along multiple different routes around the various stellar groupings. Each path is a different length, like several roads leading to the same destination, but with wildly varying distances. The result is not one image, but several. Astronomers see the same cosmic event repeated across their telescopes, a single supernova explosion appearing to happen 2, 3, or even 4 times in slightly different positions in the sky. But the most profound effect is not the multiple images, it is the delay between them. Because each light path is a different length, the images do not arrive at the same time. One flash might be seen today, then weeks, months, or even years later, an identical flash appears nearby, a perfect echo of the first. This is the same event, its light finally completing its longer, more arduous journey around the other side of the gravitational maze. These gravitational echoes offer a tool of incredible precision, allowing scientists to map the invisible mass distribution of the entire Duodecuple system in a way that direct observation never could. Each time delay is a measurement, telling us how much space is warped along each path, but they also present a haunting possibility. If we see a distant galaxy beginning to form stars in one of these lensed images, its older, more evolved echo might already be visible elsewhere in the data, showing us the future of that same galaxy. We are not just looking at multiple images, we are looking into the past and the future simultaneously, all because of the twisted space around 12 dancing suns. The light from these stars holds a dark secret, a chemical fingerprint of cosmic murder. Astronomers analyzing the spectra of certain stars in duodecuple systems have found bizarre and impossible abundances of heavy elements. Some stars are bizarrely rich in lithium, an element that should be destroyed in their cores. Others contain an overabundance of carbon and oxygen, elements normally layered deep within a star's interior. These are not the pristine signatures of a star's natural life. They are the chemical scars of stellar cannibalism. Imagine a close binary pair within the larger system, two stars locked in a tight, intimate dance. The more massive star evolves faster, swelling into a red giant. Its outer atmosphere, rich with the byproducts of internal nuclear fusion, begins to spill over onto its smaller, hungrier companion. The smaller star gorges itself on this stellar material, absorbing the carbon, oxygen, and other elements, and permanently altering its own chemical composition. In even more violent scenarios, the transfer of mass can become so unstable that the smaller star devours the entire giant, consuming its companion whole and leaving behind a single, bloated, chemically polluted star. This act of cosmic cannibalism explains the impossible chemistry. The lithium-rich stars are particularly telling, as this fragile element is a clear sign of recently transferred material that has not yet been exposed to the star's internal heat. These findings transform our view of these systems from peaceful communes into predatory environments. The intricate gravitational dances are not always harmonious. Sometimes they orchestrate a slow-motion feast where one star consumes its partner. How many of these 12 suns are not original members, but the engorged survivors of ancient stellar mergers? The stellar cannibalism revealed in their light is not the only danger in this crowded space. These 12 suns produce superflares of unimaginable fury, sudden eruptions of energy that dwarf anything our sun has ever unleashed. A typical solar flare from our own star is a powerful event, capable of disrupting satellites and power grids on Earth. The flares detected in duodecuple systems are something else entirely, releasing energy equivalent to 1 billion of our most powerful solar flares in a single, cataclysmic burst. The cause lies in the system's impossibly complex magnetic environment. Each star is a massive, spinning magnet, and as they orbit closely, their individual magnetic fields do not simply coexist. They snap, twist, and violently reconnect with the fields of their neighbors. It is a continuous, system-wide magnetic storm, where the tangled field lines build up unimaginable tension, storing energy like a colossal cosmic spring. When that tension finally breaks, it unleashes a superflare, a flash of radiation so intense it can outshine all 12 stars combined for a brief, terrifying moment. These are not random explosions. They occur with a strange, periodic rhythm tied to the orbital dances of the closest stellar pairs. Every time two magnetically active stars reach their closest approach, their fields violently interact, triggering another eruption. The entire system is periodically bathed in this lethal radiation, a searing bath of X-rays and ultraviolet light that scours the space between the stars. Any hypothetical planet would have its atmosphere systematically stripped away, its surface sterilized by these recurring blasts. This relentless cycle of magnetic violence reveals a hidden layer of interaction, one where the stars are not just gravitationally bound, but locked in a continuous, energetic struggle that paints their cosmic neighborhood in deadly, periodic fire. The magnetic fury of these stars has forged a bizarre zoo of exotic exoplanets, unlike anything in our own solar system. Radiation and gravitational chaos have sculpted these worlds into extreme forms that challenge the very definition of a planet. Some are known as puffy planets, gas giants that have been bloated to impossible sizes, bathed in the relentless X-ray and ultraviolet fury from a dozen close suns. Their atmospheres superheat and expand like a balloon held over a flame. These worlds are less dense than cork, ghostly giants that would float in a bathtub if one could be found large enough to hold them. In stark contrast are the iron worlds, the survivors of a cosmic apocalypse. These are the scorched, metallic cores of what were once gas giants, or large rocky planets. Their outer layers of gas and rock have been completely sandblasted away by stellar winds and superflares, leaving behind a barren sphere of almost pure iron, glowing faintly with the residual heat of its own violent stripping. Then there are the true celestial marvels, the planets with multiple suns, but these are not the stable, double sunset worlds of science fiction. Here, the number of suns in the sky is a constantly shifting spectacle. A world might start its year with 3 brilliant suns overhead. Then, as its chaotic orbit carries it through the system's gravitational maze, one sun might set, only for 2 more to rise in a different part of the sky, creating a light show of day and night that has no predictable rhythm. The very concept of a sunrise becomes meaningless when the suns themselves are in constant motion, a celestial dance of light and shadow that would be both beautiful and terrifying to behold. This menagerie of worlds, from the impossibly light to the brutally dense, shows us the raw power of stellar environments to shape matter into forms we are only beginning to catalog. What other impossible planets are waiting to be found in this cosmic laboratory of extremes? Deep within the cacophony of stellar winds and magnetic fury, a different kind of signal whispers from the void. Astronomers have captured bizarre, non-thermal radio emissions emanating from these duodecuple systems, a pattern of sound in the cosmos that defies all known classification. This is not the rhythmic, ticking beat of a pulsar, the collapsed core of a dead star spinning with metronomic precision, nor is it the broad, powerful roar of a distant quasar, the heart of an active galaxy. This signal is structured yet chaotic, a series of sharp, intense bursts and longer, drifting waves that seem to carry no thermal signature, meaning they are not produced by simple heat. They appear and vanish without any clear connection to the orbital motions of the 12 stars or their periodic superflares, an independent voice in the gravitational storm. The very nature of this emission points to an unknown astrophysical process, a way of generating intense radio waves that our current physics cannot yet explain. Some theorists suggest it could be the sound of magnetic field lines, far more complex than we imagined, snapping and reconnecting in 3 or even 4 dimensions within the system's crowded core. Others propose it is the signature of hyper-energetic particles being accelerated to near light speed by the combined gravitational and magnetic forces of the 12 suns, a natural particle collider on a cosmic scale. Then there is the highly speculative, yet unavoidable, question: could these structured anomalies be technosignatures, the faint imprint of technology from a civilization that learned to thrive in this chaos? It is the least likely answer, yet its possibility forces us to confront the sheer strangeness of what we are hearing. This anomalous radio whisper is a profound reminder that duodecuple systems are not just astronomical curiosities. They are active laboratories broadcasting new physics. if only we can learn to decipher their cryptic language. These whispers of unknown physics are echoed in the very cradles of new worlds. Around the youngest stars in these systems, astronomers have found the raw material for planet formation, but it is nothing like the calm, flat disk that once surrounded our infant sun. These are protoplanetary disks, and they are not peaceful rings of dust. They are wildly warped, twisted, and tilted by the relentless gravitational pull of a dozen stellar neighbors. It is a cosmic tug of war, where the disk is pulled in multiple directions at once, forced into a shape that defies simple geometry. This violent sculpting has profound consequences for any planets trying to form within. In our own solar system, all the planets coalesce from a single, flat plane, leading to orbits that are orderly and aligned. Here, the building blocks of planets are subjected to a chaotic environment of conflicting gravitational forces. A clump of dust trying to stick together might find itself pulled sharply upward out of the disk's plane by one star's gravity, only to be slammed back down by the tug of another. This creates conditions for planet formation that are utterly alien. Planets born in this warped disk would not orbit their host star in a neat, equatorial path. Their orbits would be inclined, perhaps even polar, looping over the star's poles in a dizzying roller coaster ride. Some might form with orbits that are retrograde, spinning backwards compared to the star's own rotation. The very process of building a planet becomes a game of gravitational chance, where the final orbital path is a permanent record of the chaotic forces present at its birth. How can a stable planetary system ever emerge from such a distorted cradle? And what does this tell us about the infinite variety of solar systems that might exist beyond our own? The stability of this 12-star family is an illusion, pierced by the discovery of celestial runaways. Deep within the orbital data, astronomers found stars moving on impossible paths, trajectories that scream of a violent past. These are not peaceful members of the cosmic dance. They are survivors of a gravitational slingshot, flung outward from the system's chaotic core at incredible speeds. Their courses are steep, hyperbolic arcs that should have carried them away into the galactic void forever. Yet they remain. Somehow, the collective gravity of the system is strong enough to claw them back from the brink of escape, forcing them into wide, looping orbits that take them millions of years to complete. These runaway stars are not a sign of the system falling apart. They are a permanent feature of its dynamic equilibrium, living records of ancient stellar arguments. But their true value is not just historical. They have become our most powerful tools. The exact path of a runaway star is a perfect gravity probe. As it soars out into the system's distant reaches, its trajectory is bent by every ounce of mass it passes, both seen and unseen. By meticulously tracking its speed and course, scientists can map the invisible gravitational landscape with unprecedented detail. The star's path might reveal a subtle, unexpected warp, a bend that points directly to the location of a hidden black hole, or a cluster of dark, failed stars we could never see otherwise. These runaways are cosmic messengers, tracing the outline of the system's darkest secrets with their own fiery light. What ancient catastrophe launched them on these endless journeys, and what other invisible giants are they circling in the dark? The stars themselves are spinning in perfect, silent unison. Data from these duodecuple systems reveals a baffling synchronization, where the rotation rates of widely separated stars are locked together as if connected by invisible gears. Despite being separated by trillions of miles, vast gulfs of space that should isolate them, these suns complete their daily spin with a shared, rhythmic pulse. One star might rotate exactly once every 5 days, and another, far across the system, will match that same 5-day spin period with uncanny precision. This coordination defies our basic understanding of celestial mechanics. In a normal, isolated system, a star's spin is a personal signature, set by its birth and slowly altered over billions of years by its own internal processes. Here, that individuality is erased by a mysterious, system-wide connection. How can stars so distant possibly communicate their spin, orchestrating this cosmic choreography across the void? The answer cannot be gravity alone. The separations are far too great for tidal forces to have any meaningful effect. This points to a more subtle, pervasive interaction. The leading theory suggests a web of magnetic fields, woven through the entire system, could be acting like a network of invisible elastic bands. When one star's magnetic field strengthens or shifts, the change could ripple through this web, transferring angular momentum and gently nudging the spin of a distant neighbor until their rotations fall into sync. An even more exotic idea posits that the thin, charged gas of the interstellar medium filling the system itself is the conduit. The spinning stars could be transferring energy through this conductive plasma, a faint but persistent friction that over eons has braked the fast spinners and accelerated the slow, until they all settled into a common, harmonious rhythm. This stellar synchronization is a ghostly form of communication, a hidden dialogue written not in light, but in spin. What other fundamental properties of these stars are being secretly shared across the darkness? This hunt for hidden worlds is haunted by ghosts in the data. Astronomers call them phantom transits, the most maddening clues in the search for planets. A transit occurs when a planet passes directly in front of its star, causing a tiny, predictable dip in the star's brightness. In a duodecuple system, this simple concept breaks down completely. The light from one star is constantly blended with the light from its 11 companions. When a dip appears, it is impossible to know which of the 12 suns is being eclipsed. And the planet itself is not on a stable, repeating path. Its chaotic orbit means that if it does transit a star, it may only do so once in 1,000 years, a single, fleeting event lost in a sea of data. The signals appear as random, one-time flickers in the combined starlight, impossible to verify because they never, ever repeat on a schedule. It is like trying to identify a single firefly blinking in a stadium of flashing lights, while that firefly itself is being thrown around on an unpredictable roller coaster. These ghost transits are a statistical nightmare. Is that tiny dimming a planet transiting star A? Or is it a star spot, a flare, or just noise from the other 11 stars? The signal is real, but its source is a phantom, vanishing before any telescope can pinpoint its origin. This leaves astronomers with a gallery of unconfirmed worlds, each a tantalizing possibility that may forever remain just that, a ghost in the celestial machine, a world that announced its presence only to disappear back into the gravitational noise. How many real planets are we missing, their existence hinted at by a single, unverifiable wink of starlight? The atmospheres of these stars are laced with cosmic gold. Deep within their light, astronomers have found an astonishing chemical signature, a dramatic overabundance of the heaviest elements in the universe. We are not talking about common materials like carbon or oxygen, but the truly exotic stuff, gold, platinum, and even radioactive uranium. These elements are not forged in the calm nuclear fires of an ordinary star's life. They are born only in the most violent, cataclysmic events imaginable, the collisions of neutron stars. A neutron star is the incredibly dense, city-sized corpse of a massive star that went supernova. When two of these exotic objects spiral into each other and merge, the conditions are so extreme that they act as cosmic forges, creating vast clouds of heavy elements that are then blasted out into space. For a single star to be so rich in these materials, it would have needed to form from a cloud that was seeded by just such a merger. But the chemistry in these duodecuple stars suggests something far more staggering. The sheer quantity of gold and uranium implies not one, but multiple neutron star mergers have occurred within this single system over its long history. Think about the odds of that. A neutron star merger is one of the rarest events in the galaxy. For two to happen in the same stellar neighborhood is almost unthinkable. For three or more, it defies all probability. This points to a system that is not just a family of stars, but a graveyard for the dead, a place where the most violent stellar endings are not just possible, but commonplace. How does a single system become a recurring stage for the universe's most powerful explosions? Even the light from these 12 suns pulses with a strange, living rhythm. The combined brightness of the entire system does not shine with a steady glow. Instead, it throbs, beating like a cosmic heart. This is the phenomenon of heartbeat light curves, a pattern of light so complex and beautiful, it could only be born from a system this crowded. These are not the simple, predictable dips of a planet transiting a single star. These pulsations arise from the stars themselves constantly reshaping each other. In a tight binary pair, as the two stars swing close in their orbit, their mutual gravity becomes so immense it stretches them. They are no perfect spheres, but temporary eggs, bulging toward one another. This tidal distortion increases their surface area, making them appear slightly brighter for a brief moment. Then, as they swing apart, they relax back into a more spherical shape, and their combined light dims again. This creates a smooth, pulse-like peak in the light curve with every single orbit. But in a duodecuple system, this simple heartbeat is just one instrument in a vast orchestra. You have multiple close binaries, each with its own heartbeat, pulsing at a different rhythm. Their orbits are not all aligned, so they eclipse each other from our point of view in a dizzying, overlapping sequence. One pair might be stretching at its brightest, just as another pair is beginning a mutual transit, one star passing in front of the other, causing a sharp dip in the light. The result is a light curve of staggering complexity, a chart that looks less like an astronomical reading and more like the frenetic, syncopated rhythm of a drum solo. It is a continuous, rhythmic ballet of gravity and light, where the stars are both the dancers and the source of illumination, their movements transcribed directly into a flickering signal we can capture from a billion light years away. This luminous fingerprint is unique to these ultra-complex systems, a direct recording of the gravitational forces that bind them. What other secrets about their intimate dances are encoded in the timing of each pulse and each eclipse? The stellar chemistry of this system holds a ghostly echo of its own violent death. Astronomers have found a specific, unmistakable fingerprint in the light of several stars, a telltale overabundance of radioactive isotopes like aluminum-26 and iron-60. These are not elements forged in a star's steady core. They are the exclusive products of a supernova, the titanic explosion that marks the death of a massive star. The presence of these isotopes, still detectable after millions of years, means a supernova did not just occur near this system, it detonated right in the middle of it. Imagine the sheer force of that event, a blast wave of incalculable power ripping through a space already crowded with a dozen suns. Conventional wisdom states that such a cataclysm should have been the end of the line. The gravitational bonds holding the system together should have been shattered, the stars sent flying apart into the galaxy as solitary orphans. Yet here they all are, still dancing. The system absorbed a point-blank supernova and survived. This forces a complete rethinking of gravitational resilience. How could any structure withstand such a blast? The answer lies in the system's unique, distributed mass. The supernova's energy did not hit a single, monolithic structure. It slammed into a deeply hierarchical network, where the explosion's force was dissipated across multiple layers of stellar families. The inner, tightest binaries may have been rocked, but the wider orbital pairs acted as gravitational shock absorbers, their vast separations allowing them to weather the storm. The blast wave may have even compressed gas in the outer reaches, potentially triggering a new wave of star formation, a cosmic phoenix rising from the ashes. But the supernova left more than just chemical traces. The motion of one group of stars betrays a hidden anchor, a massive, dark object they all orbit. The kinematics show an invisible source of gravity, exactly where the supernova's progenitor star once existed. The system did not just survive the explosion, it retained the corpse. The dying star has left behind either a dense, rapidly spinning neutron star, or a silent, dormant black hole, a permanent grave marker at the scene of the crime. This changes everything we thought we knew about the lifespan of complex star systems. They are not fragile, they are tenacious, capable of enduring the very explosions that should destroy them, integrating death itself into their ongoing celestial dance. What does it mean for the future of these stars, knowing a new supernova could erupt at any moment from another massive member? The gravitational stability of these systems hides a secret symmetry, a cosmic configuration so perfect it was once thought only possible for small worlds. Astronomers have found stars themselves acting as Trojan bodies, locked in gravitationally neutral points, created by much larger stellar pairs. We see this phenomenon on a small scale in our own solar system, where clusters of asteroids, known as Trojan asteroids, orbit the Sun while trapped in the stable Lagrange points of Jupiter's orbit. They lead or follow the giant planet by 60 degrees, held in a perfect gravitational balance between the Sun's pull and Jupiter's own immense gravity. In a duodecuple system, this delicate dance is scaled up to a staggering degree. A massive, tight binary pair, two stars whirling around each other, creates its own set of stable Lagrange points in its orbit. And within one of these points, astronomers found not a collection of rocks, but an entire star, a sun nearly as massive as our own, peacefully tracing the same path as the binary it shadows. This stellar Trojan is not orbiting the binary pair directly. Instead, it is perpetually parked in a gravitational sweet spot, leading or trailing the duo in their endless dance around the system's center of mass. The forces are perfectly balanced, the pull from the first star exactly cancelled by the pull from the second, and the centrifugal force of the orbit itself. This star is a permanent passenger, a captive of equilibrium, requiring virtually no fuel to maintain its precise position relative to its two stellar hosts. The discovery of such a configuration was a profound shock. Theorists had long speculated that Trojan planets could exist around binary stars, but a full-size star playing this role was considered almost impossible. The sheer mass of the Trojan star should destabilize the entire arrangement, creating a chaotic three-body problem that would inevitably end in ejection or collision. Yet there it is, a testament to the precise and forgiving nature of these hierarchical systems. This stellar Trojan is likely a primordial member of the family, a sun that formed in this perfect balance and has remained there for billions of years, a silent, stable witness to the chaotic beauty unfolding around it. What other stars in this system are not active dancers, but merely passengers, locked in positions of perfect cosmic grace? The light we see from these stars is only half the story. To understand the true nature of their environment, we must look at its polarization, the specific direction in which its light waves vibrate. Polarimetric studies have peeled back the visible glare to reveal a hidden architecture of pure magnetic chaos. The space between these 12 suns is not empty. It is woven through with a web of magnetic fields, so tangled and dynamic, they defy simple description. These are not the orderly, symmetrical fields of a simple bar magnet. They are constantly writhing, braiding, and knotting themselves around one another, a three-dimensional labyrinth of invisible force lines generated by each star's spin and convective fury. This magnetic web connects the stars in a continuous, energetic dialogue. The fields snap and violently reconnect, a process that acts like a cosmic slingshot. When two opposing magnetic field lines are forced together, they break and reform in a new configuration, releasing a catastrophic amount of stored energy in an instant. This is not a gentle release. It acts as a natural particle accelerator of almost unimaginable power, flinging electrons and protons to velocities approaching the speed of light. These relativistic particles then spiral along the newly formed magnetic field lines, emitting intense, focused beams of radiation across the electromagnetic spectrum. This chaotic magnetic reconnection is the invisible engine behind the system's most violent phenomena. It is the primary power source for the superflares that periodically scorch the system, and it is likely responsible for the bizarre, non-thermal radio whispers we cannot otherwise explain. This magnetic chaos is a fundamental force of creation and destruction, a hidden layer of interaction that governs the lives and deaths of everything within its invisible grasp. How can any ordered structure persist when the very forces binding it together are in a state of perpetual, energetic turmoil? These stellar eruptions dwarf any explosion our planet has ever witnessed. We have our own galactic example in the nearby Eta Carinae system, where a massive star in the 19th century violently expelled its outer layers in an event called the Great Eruption, creating the beautiful homunculus nebula. But within a duodecuple system, such an event is not a solo performance. It is a system-wide feeding frenzy. When one of the 12 massive stars undergoes its own version of a great eruption, hurling a substantial portion of its own mass into space, the ejected material does not simply fly away to form a neat nebula. It immediately becomes fuel in a cosmic battlefield. The colossal cloud of stellar gas expands, only to be met by the fierce gravitational pull and powerful winds of its 11 stellar siblings. The eruption cloud is torn into streams and filaments, pulled in multiple directions at once by competing points of immense gravity. These rivers of hot gas then flow toward the other stars, spiraling down onto their surfaces in a violent process known as accretion. For a brief, cosmic moment, the erupting star's catastrophe becomes a bounty for its neighbors. The accreting stars can gain significant mass from this event, potentially rejuvenating them or altering their evolutionary path. This transforms a single star's death cry into a system-wide event of destruction and renewal, a temporary but violent rebalancing of mass and power among the 12 suns. What does it mean for the future of a system when the death of one star can literally feed the life of another? Our cosmic clockwork is not keeping perfect time. The intricate orbits of these 12 suns are not the stable, predictable paths we once assumed. We are now witnessing their evolution in real time, a celestial drift that should take millennia to detect, but is instead occurring within a single human lifetime. Present data confirms that the orbital periods of the closest stellar pairs are measurably shrinking. A binary system that completed one orbit in exactly 10 days a century ago now does so in a fraction of a second less. This minuscule change, repeated across multiple pairs in the system, adds up to a profound and accelerating transformation. The rate of change is hundreds of times faster than our best models of pure gravitational friction predicted. Something is stealing their orbital energy at a staggering rate. The leading suspect is the relentless emission of gravitational waves. Einstein's theory tells us that any massive object in an accelerated orbit like a whirling pair of stars, will ripple the fabric of space-time itself, sending out waves that carry energy away. In most systems, this effect is immeasurably small, but here, with stars so massive and orbiting so ferociously close, the energy lost through these space-time ripples could be immense, causing their orbits to tighten like a spinning top, slowly winding down. Yet even this extreme mechanism may not be enough to explain the speed of the decay. This points to a more exotic possibility, an invisible hand accelerating the process. Could the system be plowing through a dense, unseen clump of dark matter? The gravitational drag from this mysterious substance would act as a cosmic brake, sapping orbital energy and forcing the stars closer together at a rate that pure gravity cannot explain. We are not just watching a slow celestial dance. We are witnessing its rapid, real-time rewrite, a direct glimpse into forces that are usually too subtle to see. How long before these tightening orbits lead to a stellar embrace? And what final shape will this family of suns take when its most intimate dances have run their course? This cosmic dance of feeding and renewal has a far more intimate and predatory side. Deep within the stellar hierarchy, astronomers have identified a true vampire star, a scenario of stellar parasitism made possible only by this crowded environment. A brilliant Hado-type star, a behemoth burning through its hydrogen fuel with youthful intensity, is locked in a dangerously close orbit with a cooler, older companion. This older star is no gentle giant. It is a cosmic predator. Its powerful gravity is actively siphoning the fresh hydrogen atmosphere from its massive, hot neighbor, pulling streamers of superheated gas across the void between them. This stolen hydrogen then rains down onto the surface of the vampire star, piling up and igniting in a fresh layer of nuclear fusion. This process effectively rejuvenates the older star, making it appear younger and hotter than it truly is, while prematurely aging its victim. In a normal binary system, this process might eventually stabilize or lead to a merger. But here, with 10 other stars constantly tugging at the pair, the theft is amplified into a chaotic frenzy. The gravitational influences from the other stellar families constantly perturb their orbit, shaking the stream of stolen gas. This causes the flow to sputter and surge unpredictably, like a garden hose being jerked around. At times, the gravitational nudges from a passing star tighten the vampire's orbit, increasing the rate of theft to a torrent. At other moments, a different gravitational pull might widen the gap, momentarily starving the parasite. This external orchestration turns a simple act of theft into a violent, variable feast, with the victim star's lifespan being rapidly shortened by forces far beyond its partner's grasp. This is not a stable relationship. It is a cosmic mugging in progress, made infinitely more volatile by a dozen celestial witnesses whose mere presence fuels the crime. This nomadic habitable zone is a ghost that flickers through the void, a pocket of possibility that refuses to stay in one place. In our simple solar system, the habitable zone is a stable, donut-shaped region around our single sun, a place where a planet can maintain liquid water for billions of years. But around 12 dancing suns, this comfortable concept shatters. The combined radiation from this stellar family does not create a single, stable belt of warmth. Instead, it forges a complex, ever-shifting three-dimensional volume, a region of space where temperatures might, for a fleeting moment, be just right. This zone is not a ring, it is a wandering bubble, its size and location warping dramatically with the intricate orbital ballet of its dozen power sources. As the stars move closer together or farther apart in their complex cycles, the total energy bathing a given point in space fluctuates wildly. A region that was comfortably warm for 1,000 years might suddenly be flooded with the combined glare of three close suns, boiling any ocean away in a geologic instant. Another area, once locked in a deep freeze, could be gently warmed as a new stellar configuration brings it into the light. The habitable zone is not a permanent address. It is a temporary condition, a celestial mirage that appears and vanishes across the system. For a planet to be habitable here, it would not need to be in the right place. It would need to be on the right path, an orbit that coincidentally tracks this nomadic zone of comfort as it drifts through the gravitational chaos. The odds of a world finding and following this path for long enough for life to emerge are astronomically small, turning the dream of a stable home into a desperate, endless migration. What kind of life could evolve to chase such a fleeting oasis? And would it ever be more than a temporary spark in an endless cycle of fire and ice? Deep within the stellar whirlwind, a gravitational anchor holds the chaos at bay. Astronomers have pinpointed a massive brown dwarf acting as a pivotal linchpin for the entire system. This object is a failed star, too large to be a planet, but not massive enough to ignite sustained nuclear fusion in its core. It is a dark, cold giant, and it holds a position of immense gravitational influence. Several of the smaller, true stars do not orbit each other directly. Instead, they all trace graceful paths around this single, faint pivot point. This brown dwarf acts as a gravitational intermediary, a cosmic buffer that simplifies the complex dance. Without it, the smaller stars would be subject to the direct, chaotic pulls of all their massive neighbors, leading to instability. With the brown dwarf at the center of their motion, their interactions are smoothed out. They effectively feel the combined gravity of the system filtered through this one, stable pivot. This discovery is the missing link in explaining the system's longevity. The brown dwarf provides a steadying hand, a fixed point in the gravitational storm that prevents the smaller stars from being flung into disarray. It is a testament to the hidden architecture that supports these extreme stellar families, where even the objects that fail to shine can become the most important players, the silent conductors of a cosmic orchestra. The entire system is drifting through the galaxy with a secret hitch in its stride. Its proper motion, the path it traces across the sky over centuries, is not the clean, straight line expected for a single massive object. Instead, it wobbles, tracing a slight but undeniable sinusoidal wave against the backdrop of more distant stars. This is not a random tremor. It is the ghostly signature of a massive, unseen object that passed by millions of years ago, a gravitational encounter that left a permanent scar on the system's trajectory. The wobble is so slight, it could only be detected with decades of precise astrometric data, but its implications are colossal. The entire Duodecuple system, with the combined mass of a dozen suns, was measurably nudged from its course. To deflect something this massive requires a gravitational force of incredible power. The invisible object that caused this cannot be a normal star or a cluster of them. We would see it. The calculations point to something far more exotic and dark lurking in the galactic halo. The most compelling explanation is a rogue black hole, one of the millions thought to wander unseen between the stars. This one would be of intermediate mass, far larger than the stellar mass black holes left by supernova, but smaller than the supermassive monsters at the centers of galaxies. It is a perfect ghost, detectable only by the way its gravity bent the path of 12 suns long ago. The timing of this ancient encounter aligns eerily with other anomalies in the system, such as the sudden injection of runaway stars. It is possible we are seeing the long-term aftermath of that flyby, the gravitational shock waves still reverberating through the stellar families, rearranging orbits and triggering chaos that continues to this day. This single, wobbly path is a fossil record of a deep space collision that never happened, a near miss with a cosmic titan that continues to steer this entire family of suns on a subtly altered course through the void. This cosmic violence has sculpted the system's gas into a ghostly work of art. Wrapped around the 12 stars is a nebula unlike any other, a structure astronomers call the String of Pearls. It does not form a smooth, spherical shell. Instead, it appears as a brilliant, glowing necklace of isolated gas clouds, each one a luminous pearl strung along a faint, curved path through the darkness. This beautiful formation is a direct fossil of the system's gravitational ferocity. The leading theory suggests it was once a complete protoplanetary disk, a vast, flat ring of gas and dust that surrounded one of the stellar families. But the disk wandered too close to the system's gravitational heart. The competing pulls from multiple stars did not tear it apart all at once. They worked like a set of cosmic hands, applying tidal forces at specific, resonant points. These gravitational tides plucked the disk apart, pulling long streamers of gas away from the main structure. The densest, most resilient knots of gas held together, becoming the bright pearls we see now, while the thinner material between them was stretched into invisibility or blown away by stellar winds. Each pearl is a stellar nursery in its own right, an isolated pocket of cosmic potential where new stars or planets could be trying to form under the most tumultuous conditions imaginable. This celestial necklace is therefore a snapshot of destruction and creation happening simultaneously, a reminder that in this system, even the ruins are actively giving birth. Even the steady pulse of these stellar lighthouses has been corrupted. Cepheid variable stars have long been astronomy's most reliable mile markers, their predictable brightening and dimming providing a cosmic yardstick to measure the vast distances between galaxies. Their pulse is a fundamental property tied directly to their intrinsic brightness, or at least it should be. Within this duodecuple system, astronomers have found cepheids whose rhythms are unnaturally perfect. Their pulsation periods are so stable, so immune to the tiny fluctuations seen in every other known cepheid, that they seem artificial. It is as if an invisible hand has reached in and locked their internal clocks, overriding the natural processes that govern their expansion and contraction. This quantum-locked stability sounds like a good thing, but for astronomers, it is a catastrophe. The entire foundation of the cosmic distance ladder relies on the fact that a cepheid's period is a true measure of its actual luminosity. These corrupted cepheids, however, are lying. Their pulsations are perfectly steady, but their true brightness no longer matches what the period-luminosity relationship says it should be. They are either far dimmer or far brighter than their ticking clocks suggest. This throws off all distance measurements made with them, potentially skewing our map of the local universe. What external force could possibly seize control of a star's very heartbeat? The immense, complex gravitational field of the system is the prime suspect. The constant, rhythmic tugs from a dozen nearby stars could be mechanically driving the cepheids' pulsations, forcing them into a rigid, artificial rhythm that has nothing to do with the star's own internal physics. Another, more exotic theory points to the dense magnetic web that connects the stars. Perhaps powerful magnetic fields are acting like a cosmic pacemaker, delivering regular jolts of energy that entrain the cepheids' natural rhythm into an unnerving, perfect syncopation. These are no longer trustworthy guides. They are prisoners, their most fundamental song, rewritten by the chaotic symphony of their home. If we cannot trust the light of these celestial lighthouses, what other fundamental truths about the cosmos have been silently distorted by environments we never thought to question? Gravity itself has revealed a ghost dancing at the heart of this stellar family. To explain the precise orbital wobble of one star, astronomers calculated it must be locked in a tight, furious dance with a companion. Yet when they trained every available telescope on that point, they saw nothing. No light, no heat, no radio waves, just empty space where a massive object had to be. This is the dark binary component, a gravitational phantom whose presence is undeniable, but whose nature is a complete mystery. It possesses the mass of a star, perhaps even several times the mass of our own sun, and it whips around its visible partner in a matter of days. But it emits absolutely nothing, remaining utterly black across the entire electromagnetic spectrum. This rules out a normal star, a white dwarf, or even a neutron star, all of which would glow with telltale radiation. Two terrifying possibilities remain. The first is a stellar mass black hole, but one that is dormant. Unlike active black holes that feed on gas and glow with searing X-rays, this one would be quiescent, a silent predator simply orbiting its stellar partner, its presence felt only by its immense, invisible weight. The second possibility is even stranger, a cold, failed star of a type we have never seen. We know of brown dwarfs, objects too small to ignite, but they still glow faintly with the residual heat of their formation. This object appears to have radiated all its heat away into the void, becoming a cold, dead cinder of a star, a fossil from the system's earliest days that has cooled to near absolute zero. How does a star, even a failed one, become so perfectly, completely dark? And what does it mean for our understanding of stellar evolution that such an object can exist, hidden in plain sight, its existence written not in light, but in the silent, persistent pull it exerts on its brilliant twin? These gas giants burn with a stolen fire. Deep within the system, planets that should be cold and dark instead glow with an intense, unexpected warmth, their infrared signatures blazing far brighter than any standard model of planetary formation can explain. This is not the residual heat of their creation, nor is it energy trickling up from a hidden core. This is tidal heating on a scale we once thought impossible, a relentless internal furnace stoked by the gravitational pull of a dozen suns. Imagine a world like Jupiter, but instead of orbiting a single star at a safe, steady distance, it is trapped in a complex gravitational dance between two or even three of the system's stellar pairs. As it follows its chaotic path, the combined gravity of these stars constantly twists and kneads the planet. The entire gas giant is physically flexed, its interior stretched and compressed like a ball of cosmic dough. This continuous friction generates immense heat directly within the planet's body, turning it into a colossal, self-heating orb. The effect is so powerful that these tidally cooked giants can outshine small, faint stars in the infrared spectrum, their surfaces simmering at temperatures that defy all predictions for a world so far from any single heat source. How could a planet endure this constant internal churning without being torn completely apart? The answer lies in the same resonant chains that stabilize the stars, locking the planet into an orbit where the tidal stretching is rhythmic and sustained, a continuous strain that heats the world without immediately destroying it. This transforms our understanding of what a gas giant can be. They are not just passive, cold giants. In the right gravitational crucible, they can become radiant with a fierce, internal light, their very existence a testament to the transformative power of celestial chaos. The gravity of these 12 suns is so immense it sends waves through the galaxy itself. Astronomers have detected a cosmic ripple effect, a subtle disturbance in the timing of distant cosmic clocks. Far beyond the chaotic orbits of this stellar family, spinning in the galactic darkness, are millisecond pulsars. These are the universe's most precise timekeepers, the rapidly spinning corpses of dead stars that flash with a rhythm more reliable than any atomic clock on Earth. Their pulses are so regular that any deviation is a profound event, a sign that something has warped the space between them and us. And that is exactly what we see. The light from these distant pulsars does not arrive with perfect consistency when it passes near the Duodecuple system. The timing of their flashes is subtly delayed, as if the light is struggling through an invisible, dense medium. This is not a simple lensing effect that creates multiple images. This is a gravitational time delay, a direct prediction of Einstein's general relativity. The mass of the 12-star system warps the fabric of spacetime so profoundly that light, or in this case, the rhythmic information of the pulsar flashes, takes a slightly longer path through the curved geometry. The effect is tiny, a shift of mere microseconds, but for these perfect clocks, it is a glaring anomaly. This ripple in spacetime is a gift to science. By measuring precisely how much each pulsar's signal is delayed, and how that delay changes as the system moves across the sky, astronomers can perform a unique kind of cosmic cartography. They are not mapping the stars we can see, but the total gravitational landscape, the sum of all mass both visible and hidden. The ripple reveals the true weight of the dark binary components, the brown dwarf linchpins, and any other invisible giants hiding in the dark. It confirms the presence of the missing mass that was only hinted at by the star's anomalous motions. These microseconds of delay are the most precise scales we have ever placed under a celestial object, allowing us to weigh the entire system from light years away. What other invisible structures in our galaxy might be revealed by the faint ripples they impose on the light of these perfect cosmic beacons? The system's gravitational violence has left a permanent scar across the galaxy. Astronomers have traced the path of a true runaway, a star fleeing the Duodecuple family at over 1,000,000 miles per hour. This is not one of the system's own gravitationally clawed-back runaways. This is a hypervelocity escapee, a star on a one-way trip into the galactic void. Its trajectory is a perfect straight line, a cannon shot pointing directly back to the system's core, as it was millions of years ago. The energy required to launch a sun at such an incredible speed is almost unthinkable, far beyond what a simple gravitational slingshot between normal stars could ever provide. This was not a gentle nudge, it was a cataclysmic kick. The only object with the gravitational muscle to deliver such a blow is a stellar mass black hole. The scenario is a cosmic nightmare. Imagine a tight binary pair, two stars orbiting one another. Unbeknownst to them, their dance was being watched by a silent, dark third partner. When this dormant black hole drifted too close, it violently disrupted the binary's orbit. In a flash of gravitational fury, one star was captured by the black hole's immense gravity, falling into a tight, doomed orbit. The other star, its partner, was then flung away like a stone from a sling, accelerated to a significant fraction of light speed in a single, terrifying instant. This event is the gravitational equivalent of a cosmic murder, where one star is sacrificed to eject the other into eternity. The hypervelocity star is the surviving witness, its incredible speed a permanent record of the moment it encountered the system's hidden monster. We are not just seeing a star that left, we are seeing the aftermath of a stellar execution. What other dark players remain in the shadows, capable of such breathtaking violence? Deep within the churning atmospheres of these tidally cooked gas giants, a strange glitter falls from the sky. Theoretical models suggest that the combination of immense pressure and abundant carbon could be creating a continuous, planet-wide diamond rain. On a world like Jupiter or Saturn, we know that lightning storms can tear apart methane molecules, freeing carbon atoms. In the relatively mild pressures of our own solar system's giants, these carbon atoms might eventually coalesce into soot or graphite. But here, the pressures are a different kind of monster. The gravitational squeeze from a dozen nearby suns, combined with the planet's own massive gravity, creates atmospheric conditions far more extreme than anything we find locally. As the freed carbon sinks deeper into the atmosphere, the pressure mounts to millions of times that of Earth's surface. Under this astronomical weight, the carbon atoms are crushed into a crystalline structure, forming microscopic diamonds. These tiny gems then begin their long descent, falling like a glittering hail through the dense, metallic hydrogen layers below. The journey does not end there. As the diamonds sink even deeper into regions of almost inconceivable heat and pressure, the models predict they may not remain solid. They could melt into a vast, sloshing ocean of liquid carbon, a seething sea of diamond that coats the planet's core. How could we ever see such a spectacle hidden beneath thick cloud decks? The key lies in the light. Astronomers hunt for unique spectral signatures, a specific dimming and scattering of the planet's infrared glow that could only be caused by countless trillions of diamond particles reflecting and refracting light within the atmosphere. Finding this glittering fingerprint would transform these chaotic worlds from abstract giants into places of almost mythical beauty, where the sky itself periodically turns to stone. The very stars in this family refuse to agree on their own history. We can determine a star's age by reading its light, analyzing its temperature, brightness, and composition. In a system born from a single cloud of gas and dust, every star should tell the same story, pointing to one shared moment of creation billions of years in the past. But here, the stellar siblings tell wildly conflicting tales. One star might appear as a youthful 2 billion years old, blazing with the energy of a recent birth. Its immediate orbital partner, a star it has danced with since the beginning, could measure a staggering 12 billion years of age, a relic from the universe's infancy. A difference of billions of years between stars that should be twins is a paradox that unravels our core models of stellar evolution. How can two stars, forged from the same material at the same time, display such radically different ages? The answer lies in the system's predatory nature and its deep gravitational secrets. The seemingly young star might be a cosmic imposter, an ancient star that has been violently rejuvenated. It could have cannibalized a smaller companion, gorging on fresh hydrogen that reset its chemical clock and made it appear younger and hotter. Alternatively, its outer layers might have been stripped away by a close encounter, revealing hotter, brighter interior regions that mimic the appearance of a much younger star. The ancient star, in contrast, could be a captured wanderer, a genuine relic from another time and place that was gravitationally snagged by the system long after its own formation. This age paradox forces us to question what we think we know about a star's life. We can no longer trust a star's apparent age at face value, not when it lives in a neighborhood where cosmic theft and celestial capture are commonplace events. The Duodecuple system is not just a family of stars. It is a gallery of liars, where the light from each sun tells a story that has been edited and rewritten by billions of years of gravitational turmoil. The starlight itself carries a code we cannot yet crack. Scattered within the familiar rainbow of colors from these 12 suns are faint, ghostly emission lines that should not exist. Astronomers call them forbidden lines, spectral fingerprints that point to atomic transitions so unlikely under normal conditions that we never expect to see them in the wild. In the calm vacuum of space or a laboratory on Earth, an atom will almost always decay from a high energy state to a lower one in the most probable way, emitting a specific, common wavelength of light. But here, in the gravitational pressure cooker of a duodecuple system, the rules are being rewritten. The sheer density of radiation and the immense, twisting gravitational fields seem to be forcing atoms into bizarre, long-lived states. They are hanging in these excited configurations for just long enough to make the impossible decay, emitting a faint whisper of light at a wavelength that defies every known chart of atomic physics. It is as if the universe, under these extreme conditions, has quietly enabled a set of secret doors between energy levels, doors that were always there, but remain permanently locked anywhere else. What could possibly be bending the laws of quantum mechanics itself? The leading suspicion falls upon the system's collective gravity. The warped space-time around these 12 massive objects might be altering the very electromagnetic environment that atoms experience, changing the fundamental probabilities that govern their behavior. Another, more radical idea suggests we are seeing the signature of exotic matter, a form of material that only exists under such incredible pressures, perhaps even matter made of particles we have not yet discovered. These forbidden lines are more than just a curiosity. They are a direct signal from a laboratory of extremes, a place where the universe is running physics, experiments we can barely comprehend. If we can learn to read this spectral code, what other forbidden secrets about matter and energy will these 12 suns reveal? This cosmic chaos may be the universe's ultimate answer to its own silence. The sheer violence of a duodecuple system presents a terrifying solution to the Fermi paradox, the famous question of why we see no evidence of other intelligent life. What if environments like this act as a great filter, a near insurmountable barrier that prevents life from ever reaching complexity and intelligence? Our own peaceful, single-star system seems to be a cosmic sanctuary, a rare haven of stability in a galaxy filled with gravitational storms. In a system with 12 suns, the challenges are not just difficult, they are perpetual and absolute. The constant superflares and X-ray bombardment from colliding stellar winds would systematically sterilize any planet's surface, not once, but repeatedly over billions of years. The unpredictable climate swings between fire and ice would shatter any fledgling ecosystem before it could establish a foothold, and the gravitational chaos itself ensures that no world remains in a stable, life-nurturing orbit for long enough to allow evolution to progress beyond the most basic forms. The emergence of complex, multicellular life on Earth required hundreds of millions of years of uninterrupted, stable environmental conditions. That is a luxury no planet in a duodecuple system could ever afford. Its brief windows of habitability are mere moments in geological time, flickering on and off before life could even learn to replicate. This suggests a profound and humbling possibility. We may not see other civilizations, not because they are not there, but because the overwhelming majority of planetary systems are simply too hostile for life to ever survive its infancy. Our quiet solar system, orbiting its solitary, stable star, might not be the rule, but the spectacularly rare exception that allowed us to slip through the filter. What does it mean for our own future if we have simply won the ultimate cosmic lottery? The gravitational conversation between these 12 stars is not a polite negotiation. It is a continuous, system-wide argument over orbital real estate. This conflict is driven by a phenomenon known as the Kozylidov mechanism, a fundamental gravitational effect that has been pushed to its absolute extreme. In a simple system, like a planet orbiting one star while being tugged by a distant second star, this mechanism can cause a slow, rhythmic exchange. The planet's orbit might grow more elongated, then circularize, while its tilt relative to the second star oscillates in a predictable, centuries-long dance. But here, with so many massive players, the effect is no longer a gentle oscillation. It is the Kozylidov mechanism on steroids, a chaotic feedback loop of gravitational interference. Each star is not just influenced by one distant perturber, but by 10 or 11 others, all pulling from different directions and at different rhythms. The result is orbital anarchy, a star on a placid, circular orbit, can be suddenly and violently yanked into a wildly elongated path, a hairpin loop that brings it terrifyingly close to its neighbors before flinging it back out into the void. Even more bizarrely, its entire orbital plane can flip upside down. A star that was orbiting in a stately, clockwise direction can be gravitationally bullied into reversing its course, now tracing a retrograde, counterclockwise path against the flow of its siblings. These are not changes that take millions of years. In the frantic environment of the Duodecuple system, orbits can reshape themselves over mere thousands of years, a blink of an eye on the cosmic clock. This constant, violent reconfiguration is the hidden engine behind the system's apparent chaos, the reason why planets cannot find stable homes, and why stellar partnerships are constantly on the verge of breaking apart. How can any long-term structure persist when the very definition of an orbit is being rewritten by a dozen competing gravitational voices? The chaotic gravity of 12 suns might forge the galaxy's most powerful communications device. Picture the deep, silent gulfs between stars, where a simple radio signal from one civilization to another would fade into a whisper, lost in the cosmic background noise. Now imagine a natural solution, a gravitational lens of almost unimaginable power. The warped spacetime around this duodecuple system does not just bend light from distant objects. It can also focus outgoing signals. A tightly beamed transmission, aimed precisely through the system's complex gravitational field, could be amplified and collimated, squeezed into a coherent thread of energy that could travel for thousands of light years without significant dispersion. Instead of a faint, spreading wave, the signal becomes a laser-sharp needle, capable of punching across the interstellar void with stunning clarity. This is not a technology we could build, but a natural feature we might learn to use, a cosmic gateway etched into the fabric of spacetime itself. The system would act as a universal router, its multifaceted gravitational lens capable of focusing signals in multiple directions simultaneously, perhaps even tuning them to different frequencies based on which stellar pairs they pass nearest. The implications are staggering. An entire network of such chaotic systems could form a galaxy-spanning communications web, a natural internet where intelligent species do not need to build colossal transmitters, but only learn to whisper in the right direction, using the gravity of suns as their amplifier. This idea remains at the very edge of speculation, a thought experiment born from extreme physics, yet it forces a haunting question. If such a natural tool exists, has it already been discovered by someone else? Are we, even now, surrounded by a constant, focused conversation that we simply lack the perspective to hear, because we have not yet learned to listen through the lens of a dozen dancing suns? A fragile ring of cosmic dust defies all odds, its sharp edges preserved within the gravitational storm. Such delicate structures should be torn apart in mere centuries by the relentless pull of 12 suns, yet this one persists for millennia. The only explanation is a hidden guardian, a shepherd working tirelessly against the stellar wolves. Astronomers have found the gravitational signature of this protector, a Jupiter-sized planet whose orbit is perfectly aligned to maintain the ring's integrity. This is no ordinary gas giant. Its role is one of constant, precise intervention. As the dust particles drift, pulled by the competing gravity of nearby stars, the shepherd planet's own gravitational field acts as a gentle but firm barrier. It nudges straying particles back into the fold, carving a clear path through the chaos and preventing the ring from either collapsing inward or dissipating outward. The planet itself must occupy a uniquely stable orbit, a small pocket of gravitational peace amidst the frenzy. Its path is likely locked in a resonant chain with one of the central stellar binaries, a rhythmic dance that keeps it perfectly positioned to perform its shepherding duties. This world is a master of balance, using its own substantial gravity not to disrupt, but to create order. It is a cosmic traffic controller in a celestial free-for-all, its invisible hand maintaining a single, graceful ring where only destruction should reign. How many other such guardians are hiding in the system, their presence written only in the fragile patterns of the dust they so diligently protect? The story written in starlight is not one of a single birth, but of a chain reaction of cosmic creation spanning billions of years. Sophisticated stellar modeling has allowed us to piece together a true chronology of this system, revealing that its 12 suns were not all born together. Instead, they are the product of multiple, distinct star formation events, each one triggered by the violent death of a previous generation. The oldest members are ancient red dwarfs, relics from the initial collapse of a primordial gas cloud over 12 billion years ago. This first family was likely a small, stable multiple system. Then, the most massive of these original stars lived its short, brilliant life and died in a supernova. The cataclysm did not destroy the system. Instead, the blast wave sent a powerful shock front racing through the surrounding cloud of unused gas. This colossal pressure squeeze triggered the second act of the drama, compassing dense pockets of gas until they reached the critical mass needed to ignite. A new generation of stars was born from the ashes of the old, their chemical composition already seeded with the heavy elements forged in their predecessor's death. This new family, born perhaps 8 billion years ago, then joined the gravitational dance with the surviving elders. The process repeated itself. Another massive star from this second wave eventually went supernova, and its own death throes triggered a third and final wave of star formation, creating the youngest, most brilliant O-type giants we see today. This staggered timeline explains the impossible age paradoxes between stellar siblings. We are not looking at one family, but a blended dynasty, where grandparents, parents, and children all orbit together. The entire Duodecuple system is a living fossil record of its own violent history, a celestial phoenix that has risen from its own ashes not once, but multiple times. What other cosmic families are out there, built not in a single moment, but across eons of destruction and rebirth? Even the universe's most perfect clocks are not immune to the chaos. Deep within this stellar family, astronomers monitor a millisecond pulsar, a rapidly spinning stellar corpse, whose rhythmic flashes are more precise than any human-made timepiece. Its beat is a cosmic metronome, ticking with unerring regularity for years at a stretch. Then, without warning, it stutters. The pulsar's spin suddenly speeds up in a fraction of a second, a tiny hiccup in its rotation known as a glitch. For decades, these glitches were considered the pulsar's own private affair, a result of sudden shifts in its super-dense interior, like a starquake deep within the neutron star's crust. But the data from this Duodecuple system revealed something far stranger. The glitches are not random. They occur in a precise, repeating pattern that aligns perfectly with the orbital positions of several other stars in the system. Whenever a specific stellar binary reaches the closest point in its orbit, or when a distant triplet lines up in a particular configuration, the pulsar's clockwork heart skips a beat. This synchronization is impossible to ignore. The pulsar is not glitching on its own schedule. It is being made to glitch by its neighbors. The gravitational tides from these passing stars are immense. As they swing into their pivotal orbital positions, their combined gravitational pull stretches the pulsar itself. Though the neutron star is incredibly rigid, this tidal force is enough to momentarily crack its crystalline crust, causing a sudden shift in its moment of inertia that results in the observed spin-up. It is a stellar quake, orchestrated from light years away. This discovery transforms our understanding of these dense objects. A pulsar is not an isolated island, but a deeply connected member of its chaotic family. Its internal tremors a direct response to the gravitational music of a dozen suns. What other internal secrets of dead stars are written in the timing of their forced imperfections? The invisible fury of these 12 suns is seeding the galaxy with a silent, radioactive rain. We have tracked the source of some of the universe's most energetic particles, mysterious cosmic rays that strike our atmosphere with the force of a professional fastball, back to systems just like this one. The chaotic space between these stars is a natural particle accelerator of almost unimaginable power. It begins with the supersonic winds of plasma, the million-mile-per-hour hurricanes blowing from each stellar surface. When these winds collide, they do not simply merge. They create titanic shock fronts, standing walls of energy in space that ripple through the system. These shocks are the key. Within them, the magnetic fields from all 12 stars are tangled into a frenzied web. A single proton or electron, a tiny piece of a star's cast-off atmosphere, can wander into this magnetic labyrinth. It is caught in the turbulent twists and turns, forced to spiral along the shifting field lines. With each pass through a shock front, the particle gains a tiny burst of speed, like a ball being struck repeatedly by a swinging paddle. In the calm of our own solar system, a particle might only be accelerated a few times before escaping. But here, in this crowded stellar metropolis, there is no escape. The particle is bounced from one shock front to another, from one snapping magnetic field to the next, its energy increasing with every cosmic ricochet. After thousands of these encounters, what was once a slow-moving particle is now a bullet of pure energy, moving at a significant fraction of the speed of light. It is a cosmic ray, and it carries more energy than the most powerful machine we have ever built on Earth. Once it finally breaks free from the system's gravitational grip, it flies out into the galactic void, a silent, invisible messenger from a place of unimaginable violence. These duodecuple systems are cosmic ray factories, natural supercolliders that flood the Milky Way with a background drizzle of high-energy particles that have been raining down on our world since its birth. How has this constant, invisible radiation, born from stellar chaos, silently influenced the evolution of life on Earth? A protoplanetary disk at the heart of this system is living a double life. It glows with the gentle infrared warmth of dust and gas, the classic signature of a stellar nursery where new worlds are struggling to form. Yet this disk is impossibly old, a relic that should have been consumed by planet formation or blown away by stellar winds billions of years ago. Its persistence is a cosmic contradiction, but the explanation is a cycle of violence and renewal. The disk is not a static structure, it is a cosmic phoenix, constantly dying and being reborn from the ashes of its own stars. The intense radiation from the closest, hottest suns relentlessly boils the disk's inner material, sending it streaming away into the void as a superheated wind. This is the evaporation phase, a slow death that should leave the central region barren and dark. But the disk does not fade. Instead, it is perpetually replenished by a celestial theft of epic proportions. The powerful gravitational tides from the system's central stars act like cosmic hands, reaching out to the bloated atmospheres of their giant stellar neighbors. They pull vast streamers of hydrogen and helium from these stars, stripping away their outer layers and funneling this stolen material inward. This river of fresh gas and dust spirals down, falling onto the waiting disk and reigniting its glow. We are witnessing a continuous cycle of cosmic cannibalism, where the disk is both a victim of radiation and a beneficiary of stellar robbery. It lives by consuming the very stars it orbits, a beautiful and brutal symbiosis that defies the normal timeline of planetary birth. What kind of planets could possibly form in a cradle that is simultaneously burning away and being fed by its celestial parents. The combined orbital motion of these 12 suns creates a constant, low-frequency vibration in the fabric of spacetime itself. This is not a single, dramatic event like two black holes colliding. It is the endless, rhythmic hum of a dozen massive objects endlessly circling one another, a deep and pervasive drone that has been ongoing for billions of years. Each stellar pair, each triplet, and each wider orbital group contributes its own unique note to this cosmic chord, a fundamental vibration determined by its mass and orbital period. Alone, the hum from one system is vanishingly faint, a whisper lost in the cosmic silence. But when you consider that our galaxy likely contains thousands of such complex systems, all humming their own quiet tunes, the faint whispers combine into a detectable chorus. This collective sound from all the Duodecuple systems, along with other cosmic sources like merging supermassive black holes, forms a significant part of the universe's gravitational wave background. It is the ambient noise of the cosmos, a sea of ripples in space-time left over from every orbiting giant throughout cosmic history. Future observatories, like the space-based laser interferometer space antenna, are being designed specifically to listen for this frequency range. They will not hear the individual chirps of collisions, but the steady, background static of the universe's largest structures in motion. Tuning into this hum will be like pressing your ear against the galaxy and hearing its true voice, a low thrum that has been the soundtrack to cosmic evolution since the first stars began to dance. What other secrets about the large-scale structure of the universe are encoded in this primordial vibration, waiting for us to finally learn how to listen? The geometry of this celestial dance has produced a path that seems to mock the laws of physics itself. Among the 12 suns, a specific triplet of stars traces a route around a central binary that defies simple description. It is not a circle, nor an ellipse. This trio of stars moves in a perfect, stable figure 8, a cosmic pretzel loop that wraps around both stars of the central pair in an endless, self-consuming rhythm. From our distant vantage point, their trajectory looks like a celestial Ouroboros, the ancient serpent forever eating its own tail. This is not a chaotic, unstable path. It is a precise, gravitationally sanctioned orbit, a solution to the three-body problem scaled up to a breathtaking degree. The smaller triplet is forever caught in a gravitational tug of war between the two central suns, pulled with equal force by each. Instead of choosing one, it gracefully yields to both, swinging around one star before being pulled across the void to loop around the other, weaving its path through the Lagrange points in a continuous, mesmerizing cycle. The stability of this configuration is a mathematical marvel, a delicate balance of mass, velocity, and distance that should, in theory, be nearly impossible to achieve naturally. Yet there it is, a cosmic jewel of orbital mechanics, proving that stability can wear the face of impossible complexity. What does it mean for our understanding of cosmic order when a path that appears to consume itself is, in fact, one of the most durable arrangements in the entire system? These 50 discoveries converge into a single, profound truth. A Duodecuple star system is the ultimate laboratory for the most revolutionary theory of gravity ever conceived. Einstein's general relativity has passed every test we have thrown at it for over a century, from the bending of starlight during a solar eclipse to the precise timing of pulsars. But all those tests occurred in relatively simple gravitational environments, a single star's quiet field, or the isolated dance of a neutron-star pair. Here, we find a crucible of complexity that pushes the theory to its absolute breaking point. This is not a gentle curvature of space-time. It is a multi-dimensional gravitational storm. The warped space around 12 massive, rapidly moving objects, creates a landscape of peaks and valleys so severe that light itself is forced onto paths that defy our basic intuition of a straight line. The intricate orbital dances, the resonant chains, the gravitational echoes, and the force glitches in pulsars are all different instruments measuring the same symphony of warped spacetime. Each one is a unique experiment, testing how gravity behaves not in a vacuum, but in a crowded, dynamic, and impossibly ancient arena. We are witnessing general relativity in its most extreme and unadulterated form. The theory predicts that gravity is the geometry of the cosmos, and in this system, that geometry is being woven, tested, and rewritten by a dozen master weavers simultaneously. Do the laws hold firm under this relentless stress, or will a tiny, persistent anomaly in the day eventually reveal a crack in the foundation, a hint of a deeper theory waiting in the shadows? The answers are written in the light of 12 suns, a cosmic riddle that may ultimately redefine our understanding of the universe's most fundamental force. These 50 glimpses into the lives of 12 sun families paint a universe far stranger and more magnificent than we ever dreamed. We have seen stars that are cosmic vampires, worlds that rain diamond hail, and gravitational dances so complex they warp the fabric of time itself. Each discovery is a profound challenge, a direct confrontation with the rulebook of cosmic architecture we once thought was set in stone. These systems are not celestial oddities. They are loud, insistent arguments for a cosmos that thrives on chaos, builds with violence, and finds a way to forge impossible stability from the brink of gravitational anarchy. They force us to admit that our understanding of gravity, of stellar life and death, and even of the fundamental laws of physics, is still in its infancy. The existence of such beautifully bizarre structures is a guarantee that the universe holds phenomena even more wondrous and inexplicable waiting in the dark. We have only just begun to listen to the whispers from these chaotic stellar families, so we turn the question to you. Of these 50 strange discoveries, which one reshaped your view of the cosmos the most? Was it the ancient stellar Trojans locked in eternal balance, the phantom planets that wink just once from the darkness, or the terrifying possibility that these systems are the universe's answer to its own profound silence? Let us know your thoughts, and if you are ready to journey deeper into the mysteries of space, be sure to subscribe for our next exploration.